So last time we were talking about the Chrial Lagrangian as another example of an effective field theory to illustrate some of the tools of effective field theory that we didn't meet when integrating out heavy particles. It was an example of a bottom-up effective field theory. So we were constructing it from the bottom up for the most part. That's how one should think about it. There was several things in our program to understand from Chrial perturbation theory, and we kind of got halfway through. So we wanted to understand nonlinear symmetry representations, and we went through how you could think about linear representations and making changes a variable and putting the Lagrangian in a form where you could see where the nonlinear realization was coming from very explicitly, as well as another way where we constructed it from the bottom up, thinking about parametrizing the coset. And then we started talking about loops in Chrial perturbation theory, and I gave you this example of this loop here. So we constructed the Chrial Lagrangian. That's what I've written here. In terms of this sigma field, this is the nonlinear version. Sigma field, exponential of an M field. M field has the pion fields in it. I rewrote it in a little bit of a different notation, which will be useful today, where I introduced this thing called chi, but f squared over 8 chi is just mq. So it's just a rescaling. And I just wanted to have the same kind of prefactor here and here. That's why I did that. The power counting is in p squared derivatives or m pi squared, which is the same as mq. And the reason that m pi squared and mq count the same is there's this relation between m pi squared and the quark masses. And then we started talking about loops, and we said that if we looked at this loop, the result for this loop diagram would be a factor of p squared or m pi squared times a factor of p squared or m pi squared divided by 4 pi f. So we had associated, so this is what the lowest order, this is the same size as the lowest order, so the suppression factor is this. So we can say that loops are suppressed by p squared over some scale lambda chi squared, which is the scale of our expansion, and we can associate that scale to 4 pi times f. OK, so we're going to continue with that story, unless there's any questions from last time. OK, so we want to use dimensional regularization. And if we use dimensional regularization, we can think about having an MS bar scheme. So how do we do that? It's a little different than gauge theory, but the idea is exactly the same. So we look at the dimensions of objects. This capital M, supposed to be a capital M, is like a scalar field, so it has dimension 1 minus epsilon. The decay constant, then if you look at it, which is the coupling, has to have dimension 1 minus epsilon 2. And you can see that because this exponential better be the exponential of something dimensionless, so that whatever the dimension of M should cancel by the dimension of F. And then that works out with the measure as well, which has a ddx. So you can say, therefore, that F bar, just like you did for a coupling, a gauge coupling, you can say F bar is some mu to the minus epsilon times F. And if you want to do the same thing for the second term, although I've put the v0 inside the, sorry, there's something missing in my equation. There's a v0 here. So before last time, we'd written this equation as v0 up front and then mq inside. And I just rescaled it to this chi. OK, so you can think either in terms of chi. Chi is kind of absorbing the parameter along with the mq. But they're equivalent things. So you can think of also doing a rescaling that gets the dimension of this term right. And the thing that you want is this. That v0 would then be mu to the minus 2 epsilon to compensate for the fact that the first term had f squared and the second term just had a v0. So that's just dimension counting. There's also no mu's in physical quantities like the pion mass, which is an observable, which has just a definite value. And there's also, in Chrial perturbation theory, no mu's in the quark mass. So when you look at V0 over F squared, if you look at it bare, that's the same as renormalized. The other thing that's different about this than in a gauge theory is in the gauge theory you'd have a z. You'd have g bare is equal to u to the epsilon times g, but then you'd have a zg. But in Chrial perturbation theory, the way that the loops work, the loops aren't renormalizing the leading order Lagrangian. The loops are renormalizing something else because they ended up being suppressed. So you don't need counterterms here for the leading order Lagrangian. That's why I didn't put a ZF or a ZV0 here. OK, but when you do this loop, you do get ultraviolet divergences. So you get a 1 over epsilon divergence if you're using dimensional regularization, and it comes along with the log of mu squared. And then it'll be divided by some scale that you have in your loop, like an external momentum p squared, or it could be the pion mass. Both of those will show up generically. And in the way we're doing counting, the way the loops are showing up, if I combine together the factors that I told you about here, it's either p to the fourth, 4 powers of p, or 2 of p and 2 of m pi, or 4 powers of m pi. So to cancel that 1 over epsilon, we need a counterterm. But it's not a counterterm in that Lagrangian. It's a counterterm in the higher order Lagrangian. So we're not done by just calculating the loop. We have to actually include some higher dimension operators that are the same order in our power counting. So we'll talk about SU3 a little later. I'll start out by talking about SU2. In SU2, the form of that Lagrangian with higher order terms is just taking what we had before and just going to higher dimension. So we could have 2 more derivatives. One way of doing that is taking what we had at lowest order and squaring it. Another way of doing it would be to take and contract the indices a little bit differently. So I could do it like this. The trace is cyclic, so I can move things around from back to front. But I could have mu nu in one trace and mu nu in another trace rather than just contracting within the trace. That's another possible term. And there's a bunch more terms, which I decided to wait and enumerate when we do SU3 to give you a full enumeration. These additional terms you can build from one MQ, which means one of these chi fields or chi objects, and 2 partials. That's one possibility. Or 2 MQs, because each MQ counts like 2 derivatives. So there's some other terms that we could build that are analogs of this term. You could square that term, for example. That would be a possible higher order term. And so these coefficients of this Lagrangian are what we need to cancel off the divergences. So the counterterms that we have that renormalize these loop graphs come from this Lagrangian. So the theory is renormalizable in a if EFT sense, order by order in its power counting expansion. When you go to order p to the fourth, you have to consistently put in everything that's order p to the fourth. That includes the loops, which are p to the fourth, as well as new local Lagrangian interactions.
Is that a choice to not renormalize the f bar and d bar?
They just don't get renormalized.
But why couldn't I just multiply that by 1 plus order p squared by
yeah, so
times delta?
to make you want to try to make a different scheme for
I'd
them.
screw up the power counting.
So effectively, you could screw up the power counting by doing that. So you could, let me tell you what you can do. You could put a 2 here, right? But you don't really have much more freedom than just multiplying by a number.
So I can't multiply by 1 plus p squared over s squared or something?
Yeah, that would be screwing up the power counting, and effectively that's, what you wouldn't be multiplying by p squared, you'd be putting derivatives in, right? Because there's no p, and so p is not something that you're allowed to multiply by.
So that's the only thing that's stopping me though is derivatives.
You could put derivatives in, but then that's equivalent to something here, so you have to ask what you're doing because you're mixing up things.
Okay.
Yeah.
There's definitely a better way to do it. I was just wondering if there's sort of freedom.
Yeah, there's no freedom, really.
Good.
Why you don't get the renormalization of the kinetic term, like from a diagram?
Because all the loops end up being suppressed by p squared or m pi squared. So if you write down any diagram and you think it might give something here, even if it's a 2-point function, it just doesn't. And
you are including p to the 4 terms, right?
That's right. So these terms. So if you want, you could think that some terms here are kind of corrections to the kinetic term. If you derive the equation of motion and you include L and that L and this L, right? But this Lagrangian here does not get there's no loop corrections to this Lagrangian. There's no corrections to this lowest order Lagrangian, and that's because the loops are all suppressed by totally different than gauge theory. Loops are suppressed by p squared or m pi squared, so they only renormalize some higher order things, and we don't have to worry about really thinking about f. I mean, the way I've talked about f here and the factors of mu is just in order to, see where these factors of mu come out here. But what actually happens is that you get 1 over epsilons that are canceled by the counter terms here, and there's no kind of change of, no need from a renormalization perspective to sort of change your definitions here. People play with different definitions, but it's like they use f squared over 4 instead of f squared over 8. That's the extent of what people do with playing with the leading order Lagrangian.
So it's the same thing with the loop. That thing is not renormalizing that.
Both of them are not, yeah. Yeah. So loops that you build out of these interactions end up renormalizing these terms, which is kind of neat.
That's just because there's derivatives and capacity that's unable to.
Hmm?
That's just because there's everything's derivatively coupled.
Yeah, I mean, we'll prove in a minute like a general power counting formula that tells us how to organize all this. So for now, you can think of it as an observation, but we'll build it into a general formula that tells you sort of how you would organize the power counting and renormalization of this theory to all orders in its expansion in a minute.
So when you write down all these terms at order P4, does that include all the counter terms you need?
Yeah, that's right. So once I've enumerated all the terms, which I will do for you with SU3, so it includes things like this and things like this as well, then those are all the possible counter terms that you could actually need to renormalize any of the one-loop diagrams that you could generate with the leading order Lagrangian. And you know that by power counting. Once you know the loops are that order and you've included all local interactions, then you're done. So there's things I didn't write down there. So just comment about that. So what is the equation of motion here? So little more complicated because we have the sigma field, but you can work out that the equation of motion is the following. And I've given you some reading to show you, so you can read about a derivation of this equation, which takes a little effort. So the leading order equation of motion basically allows you to get rid of partial squareds on the sigma. And that's why I've always written the partial, one partial on each sigma. So that's what you should think of this guy doing. There's also some SU2 identities that have been used, even in what I've written, because you could think of having other types of traces, like this one, for example. Like, instead of having trace squared, I could have the following. Just put everything in one trace. I always have to alternate sigma, sigma dagger, sigma, sigma dagger, because del mu sigma, sigma dagger is 0, because sigma, sigma dagger is 1. And that provides an identity that I'm also able to use. And so I want to have sigmas and sigma daggers next to each other to avoid having. So that's one thing. Sorry, chiral symmetry means that sigmas and sigma daggers should be next to each other. This is an identity that I can also use to simplify things, so that allows me to move things around. And this operator, though, in SU2 is actually related to these two. It's not unique because of the structure of polymatrices. You have a formula which you can work out, which says that this guy is actually a half of the trace squared. And there's another one if you did. This guy, he also can be related to those two guys over there. Okay, so there's a bunch of things that went into even writing down the level of information that I told you. You could think there's more things, but then when you enumerate all the possible things that you can do, you find that those more things are related to these things. So you really want to construct a minimal basis, and there's some things that go into doing that. So at order p to the fourth, as I said, we include both loops. And those loops will have terms like p to the fourth log mu squared over p squared. And we include terms like the L1 and L2, which are p to the fourth type interactions. Once I take out the counter term, the renormalized coupling is mu-dependent, just like the gauge coupling. This just comes from a 4-point interaction with the Li. And the mu-dependence, by construction, is canceled between these two things. The divergence is canceled from the loop is canceled by the counter term, and correspondingly, the corresponding statement, if you want to make it in terms of mu, is that the mu dependence that is tightly tied to that 1 over epsilon is canceled in the renormalized quantities. Okay, so there's these two contributions. They're both mu-dependent, and that mu-dependence cancels. So the way that you should think of this is you should think mu is a cutoff. It's not a hard cutoff, but it is a cutoff. And what the cutoff is doing is dividing up infrared and ultraviolet physics. In this case, the low energy physics is in the matrix elements, in the loops. Where we have our propagating low energy degrees of freedom, which are the pions. And the high energy physics is in the coefficients, as usual, they're both mu-dependents, and you can think of that mu-dependent as a cutoff that divides up how much of the physics goes into those low-energy loops, how much of the physics goes into the couplings. So the difference between this and integrating out a massive particle is not the physics of where things go, because the low-energy physics always goes in the matrix elements, the high-energy physics goes in the couplings. The difference is that here we think that the way that you should think of it is that we can calculate the matrix elements explicitly, because our theory is in terms of the right degrees of freedom to describe long-distance physics, which are the pions, and then the coefficients are the unknowns. That's the way in which it's different. And that's really kind of the difference between bottom-up and top-down.